Okay, so this video is going to help us understand a little bit about improper integrals and what those are, and we're going to look at kind of two main classes, which each have about 3 different cases to examine. So improper integrals are things that have something in the integrand, or I guess in the bounds, that are not sort of quote-unquote proper, like, they're not nice, they're not things that we're used to. So we're used to things like the integral from 1 to 3 of x squared dx. And this is great because 1 and 3 are numbers, as are anything in between 1 and 3 that we can plug into x squared and get back values. And when you look at the graph of that, that's all very standard. You could certainly draw x squared from 1 to 3, right, and calculate the area of this with no question. Looks like I didn't do a great job of drawing that, but that's all proper and great. So the idea of an improper integral are things that have something in the bound that's not quote-unquote proper. So let's look at our first case. So the first case would be something that looks like this: the integral from a to infinity of some function f of x. So now we have an infinity in our integral, and that's not proper, right? We can't actually do that. That's not a real number. We can't actually calculate the area officially doing it that way. So what we can do is take the limit as t goes to infinity of the integral from a to t. So it's a way to sort of rewrite this integral as something that we can actually understand and actually read. So, and that actually means something to us as opposed to infinity, which isn't a number and doesn't mean anything in the context of this. So we rewrite it and talk about the limit as t goes to infinity, and that's something that we can understand and appreciate. And you can do a similar thing if you have maybe an integral from negative infinity to b. And here you would take, again, the limit as t approaches infinity from, or I guess negative infinity, from t to b of f of x dx. So just make sure you get your negative in there, negative infinity. And then the last example would be if you have, we can have infinity in the top bound, we could have a negative infinity in the bottom bound, or we can also have an integral that has infinities in both the top and the bottom bound. So we want sort of the area under the curve across the whole sort of x-axis. So in this case, we could split this into 2 integrals. So we're going to go from the limit as t approaches negative infinity from t to some a, f of x, and remembering our rules of limits or integrals, we'll also then go from a up to some s. And here we'll take the limit as s goes to infinity. And here, a is just any real number that you want. So that's the idea, is that we pick a number so that we can actually split it into 2 nice integrals and take the limit of each in the appropriate way. In particular, as t goes to negative infinity and as s goes to infinity. And notice that we're using 2 different variables here to help us later on so that we don't get confused with the fact that t is negative infinity and s is positive infinity. So we're using 2 words now, convergent and divergent. And convergent, we're going to mean this is any integral that gives us a value back. So an actual numeric value. And an integral is divergent if the limit that we take goes to infinity or does not exist. So this situation, right, is any sort of improper integral that is going to give us an actual number back when we actually take the limit. And this is divergent, are things where the limit actually doesn't exist or we get plus or minus infinity. So those are kind of your 2 different words that we'll use when we talk about integrals. Convergent means they're going to a number. Divergent means they're going to infinity or don't exist. We're now going to look at 3 more cases. We had the 3 infinite cases, and now these are 3 cases where we have discontinuities. So we have 3 more cases of improper integrals that are important. The first one will be an integral from a to b of f of x dx, where f is continuous on a to b. So i.e. it's discontinuous at a. So in other words, we can't actually plug a into this function, so there's going to be a discontinuity, and if we're looking at trying to find the area under that curve, we don't want to use the value right at a, so we'll take the limit as t approaches a from t to b of f of x dx and calculate that instead. Similarly, if f is continuous on a to b, but not at b, we would turn the integral from a to b of f of x dx into the limit as t approaches infinity of the integral from a to t. And then the last example, let's say f is discontinuous at x equals c, and c is between a and b. So we'd have the integral from a to b of f of x dx, and it wouldn't necessarily be 100% clear that that's improper, but because this discontinuity occurs in the middle of this integral, we have to split the integral at that discontinuity. So we'll take the limit as t approaches c of the integral from a to t of f of x dx, and then add the integral from t to b of f of x dx. And we'll take that limit as t approaches c. So these are our 3 different cases of improper integrals. There's also another video of a few examples of improper integrals if you also want to see that one.